Hi. Well, it's extremely nice to be able to be here and help Ram celebrate his 60th birthday. He was always so much more intellectual and mature than me. I can't imagine you're only 60. It's just incredible. But so I'd like to tell you some stuff. I hope that I don't take a very long time, and I certainly don't intend to give you any details. This is a little bit loud. I certainly don't intend to give you any details about anything, but I hope to tell you a story of some things, which I hope that you'll find kind of interesting. It's, as you know, it's been a passionate pursuit of many people for many years to figure out some subconvexity bounds for various L series, and I'm afraid that I have fallen into the trap of going down this path as well. I used to think of math as a very uncompetitive business, but I'm afraid when you start doing subconvexity bounds, that's not the story. It's one mathematician for themselves, and so the particular thing that I want to tell you about here is, well, consider the following. Suppose F and G are holomorphic cusp forms on GL2 with expansions. F of Z is A of n to the k minus 1 over 2 e to the 2 pi I nz, and suppose G of Z is exactly the same. What's that? Oh, the sum. I mean, the sum was implicit. Good grief. And then sum n bigger than 1 e to the 2 pi I nz. I really think this is slightly too loud. Could you turn down the volume a bit? How is this? Okay, so the actors on the stage are going to be this two holomorphic forms, F and G, and I will also take U sub J to be an orthonormal basis for Moss forms. And I want them to have Fourier coefficients. I will not waste time writing down the Fourier expansion, but I will just say the Fourier coefficients are rho sub j of n, which will be, I'm going to think of as rho sub j of 1 times lambda j of n. And let's consider the whole thing will be over SL2Z, so I don't have to think about level or new forms or anything like that, though I believe everything I say applies to general level. So we have an orthonormal basis for cusp forms. Fourier coefficients are these. These are the Hecke eigenvalues. And these are the the first coefficients. These are rather large, and these are on the order of size e to the pi over 2 absolute value of Tj, where Uj corresponds to eigenvalues of the form a half plus or minus Itj. So rho j of 1 would be rather enormous. This is the Hecke eigenvalue. And what I want to consider in this context are the Rankin-Selberg convolutions of F with such Uj and with G with such a G with such Uj. So I want to consider L of a half F with Uj, and I want to actually consider L of a half with G times Uj. I want to weight this in the following way with minus tj squared over t squared. I want to sum over all the t sub j's. And so as you could imagine from this, this is essentially this is a smooth average of the products of these two L series for eigenvalues basically up to capital T. And the question is it possible to find a moment, to actually find a formula for this in terms of the main term plus an error term? I don't think it's been done before in this aspect. I looked as hard as I could, which isn't, I confess, that hard. But I did look through the literature and didn't see any traces of anything like that. In fact, I only found a reference to one fourth moment. This counts as a type of fourth order moment because there's actually, yeah, that's right. Yeah, this counts a fourth moment of a GL2-like thing. This is like two GL2 forms. This is like two GL2 forms. There is one existing fourth moment formula that I know of the form L of a half uj to the fourth is asymptotic to t is actually equal. No, is actually. I cannot remember if it's asymptotic or equal to t. I cannot remember. I'm blanking on that. But there's some sort of fourth power result for these things due to Ivich. But for something like this, I don't think it's been done before. And it turns out that the answer is something like this: a certain constant times t squared times a polynomial in log t plus an error on the order of t to the 1 plus theta plus epsilon, where theta, as usual, denotes the closest progress that's been made so far towards the Ramanujan bound in the Archimedean sense. So in particular, in this case, it's well known that the best bound over the rationals is 7/64. So this is a very satisfactory error for such a thing. And one of the reasons, and p of log t, this is degree equal 2 when f is not equal to g, and the degree equal to 3 when f equals g. And one of the main reasons why one considers moment formulas like this is one is really after the notion of an upper bound for an individual one. So what one really is hoping for is a result of the form what one really hopes for is a result of the form L of a half f cross u sub j is less than tj to the something plus epsilon. And then the race is on. The game and the race is on. Alpha equal to 1 is the trivial convexity bound. Now I have to remind myself a bit of the history of this thing. The first person to have any sort of progress on an estimate like this was Sarnak in about 2001. And let's see. And Sarnak got this with alpha equal to 526 601sts. He didn't actually get this TJ. He did it with weights, but an argument that translated if you did over the same argument with Moss forms into this. answer. And then Lee and yeah, not very good on years, but did t to the 15 plus 2 theta over 16 plus epsilon. Or in other words, this was alpha, 15 plus 2 theta over 16, where theta, as before, is the best progress towards the Ramanujan bound. So using theta equal to 7/64, this came to alpha equals 487/512. This is typical of the sort of strange numbers that one gets in this business. But then, a couple of years later, these two and Lau teamed up and got a profoundly different sort of result. Well, I don't need to copy over the thing. They got alpha equal to 2/3, independent of the independent of the Ramanujan conjecture, and that's usually considered the best possible result in this day and age for this kind of thing, because this result 2/3 equals 2/3 of 1, which equals 2/3 of the convexity bound. For the Riemann zeta function, for zeta of S, the convexity bound is 1/4, and 2/3 of 1/4 is 1/6, which was gotten by Weil, and is the famous Weil estimate for the size of a Riemann zeta function in the t aspect, that is, along the critical strip. And then in the years since then, a 6 has been surpassed by a little bit only in the case of the Riemann zeta function. Nobody has gone past the 6, or nobody has gone past 2/3 convexity under any circumstances, I don't think. But what we want to say is that I have to mention everything I'm talking about is joint work with Min Lee, who is a postdoc at Brown right now and is also looking for a job and is utterly wonderful, as is that other student that I mentioned, and even a third student who I didn't mention, but that doesn't stop him from being wonderful. So anyway, it's all joint with her. What we seem to obtain is alpha equals 1/2. So this is a little surprisingly strong. But as far as you could tell, this is the answer. I guess I won't be completely amazed if I suddenly find that a line in our proof consists of the equivalent of 1 = 0. But at the moment, we've gone over this many, many times, and there are elaborate error checking things in this proof. In the way the proof, which I'm going to describe, not the proof, but I'll describe the philosophy behind the proof to you. The way the philosophy behind the proof works is you end up with tremendously complicated formulas here and tremendously complicated formulas here. And in order for the whole structure of everything to be right, this has got to exactly match up to this. Believe me, the chances of it matching up to that when you actually compute it are practically 0. But it actually checks when the formulas are done carefully enough. The checking actually happens, so that we have a certain amount of confidence that we're not making a mistake here. what I really am interested in is the story of what we're trying to do here, why, of the approach that we're taking, because the approach is far more interesting than the actual result. And the approach promises to lead in a number of other interesting directions. So, it all starts with the Kuznetsov trace formula, which looks something like this. These rho j's of m's and n's are, as I mentioned before, coefficients of an orthonormal basis of Moss forms, u sub j. You divide by hyperbolic cosine of pi tj, which has the effect of exactly canceling out, or almost exactly canceling out, the rho j of 1 contributions of these things. So what's left is essentially just the lambda, the Heck eigenvalues here. That's the way you should think of it. And I will, this is usually, I'll abbreviate this, the usual form, the usual way in which you see the Kuznetsov trace formula portrayed is with a general test function, h of tj in there. And the test function that I'll particularly be using in this case is e to the minus tj squared. And this thing, this is known as the spectral side. And this is equal to delta mn T10 hyperbolic tangent of pi t h of t. It's a little easier to write h of t than dt, plus the sum over c, bigger than or equal to 1, of s mnc over c, 2I over pi, j sub 2it, 4 pi square root of mn over c. Almost there, don't worry. H of t times dt over hyperbolic cosine of pi t. So this is the Kuznetsov trace formula. This side is called the arithmetic side. And I have to confess that the first time I saw this, I thought that nothing in the world would induce me ever to have anything to do with something that looks as ridiculous as this. I found the j functions in particular to be extremely intimidating. However, it turns out that when really, every time you see a terrifying function, if you think of it as a couple of inverse Mellin transforms of a ratio of gamma factors, that seems to be, I mean, somehow things get considerably less intimidating. And in particular, that's the way it turns out to be advisable to think about this j function here, a bigger than or equal to 1. See, this is what you do with the Kuznetsov trace formula. You use, this is a sum over all the u sub j's, but for any m and for any n, and you're free to multiply the whole sum by anything you like, as much as you like, and add it up, as long as you could hopefully still keep track of what goes on the other side. And what happens here is if you do this, this ends up being the sum rho j of 1 squared L of a half F cross uj. Oh dear. Okay. Let me just rub this out and write something that replaces it. This ends up being this times L of a half G cross uj over cosh pi tj. So I have assembled the thing that I'm interested in on the left-hand side by multiplying by these two things and adding them up. And now what's necessary is to do the same thing to what I just erased. And the reason I erased it is because once you do that, you get, once you do that, you after a tremendous, after a never mind how much work everything. After not too much work, you end up with this interesting thing. L of S plus W F cross G 1 over pi squared T tan pi T H of T dt. This is the diagonal term. This is S plus W of F cross G. So in other words, we get this, and then we get plus a very odd-looking thing, which I'm going to abbreviate so it's bearable. I'm going to abbreviate 2 over pi I times the integral over a real line that goes a vertical line passing through real part 1/4 plus 2 epsilon of another integral of something going over minus 1/4 minus epsilon. And then we have our function h of u, well, this is our test function times u. We have a function which I'm certainly not going to describe, which is a gigantic, not gigantic, but a relatively large ratio of gamma functions in the two variables u and v. Certainly not worth writing down. The whole thing is divided by the cosine of pi u. And here comes, this is the fun part, zeta of 2s, the sum of b of m over m to the w plus v. U and v are the two variables of integration of these two things. So b of m over m to the w plus v times a sum of s mn of c a of n over n to the s plus v c to the 1 minus 2v. Okay, and what is this s? S is the Kusterman sum, equals the sum over alpha mod c, alpha relatively prime to c, of e to the 2 pi I m alpha plus n alpha inverse over c.
Did you specialize to double half or s equals half?
No, I have not. You're right. Pardon me. You're right. Thank you. Yes, many people use the approximate functional equation. What I feel much happier doing is using general variables s and w, and everything will converge absolutely if the s and w are large enough. And then after a long time has passed, you could generally analytically continue the right-hand side back to whatever you want. And you've gotten past, I really hate the approximate functional equation. No insult intended to people. I know there has lots of friends. But what I want to look at here, yes, in a final du dv. Actually, to be completely honest, it's dv du. Okay, so what could possibly be the point of writing such a complicated formula on the board in the middle of a lecture? I usually, I usually can't stand it when people do stuff like this. Don't worry, nobody here has done that yet. But what I want to stare at this and philosophize a bit. Okay, so horrible long formulas are fine as long as you actually philosophize with them and don't just compute with them. So take a look at this. This is the thing you want, okay? It's got two variables, s and w, which you would like very much to analytically continue back to s equals a half and w equals a half. That's going to depend upon your ability to understand what the right-hand side means. Now, this right-hand side, well, if you think about if s is large, then the sum over n will certainly converge. And if v is negative, which it is, it's that minus a quarter, the sum over c will certainly converge. So if you look at this in the correct, if you look at this exactly as I've stated it, this is a convergent series, and unbelievably, it remains convergent while as you bring s back to a half and w back to 1. So you could stop here if you wanted to. But you don't get a very good answer if you do that. You get and this is sufficiently complicated. This is part of your main term. This diagonal term is part of your main term, but part of your main term also comes from this. And if you stop here, it gets very hard to see that. Now, where does this come? What, sorry? The Bessel function is buried inside of this. We ended up with two. We get one of the Bessel. I don't know if you're familiar with the Bessel function to be represented as a Barnes integral, an inverse Mellin transform of a ratio of gamma functions. So I've done that, and part of it comes from there, and the other comes from somewhere else. So I believe there's a whole story of working with this kind of thing, and I'm kind of curious to get at the history of the story. Because back in 1978, Goldfeld told me about a very interesting thing that he did operating on a series like this, operating on this kind of thing. And a way of taking these Kloosterman sums and futzing around with them properly so that they turn miraculously into Ramanujan sums. And the Ramanujan sums disappear and leave in their place a shifted divisor function. And so Goldfeld used this in 1978 in a paper of his called an Analytic Arithmetic Theory of Poincare Series. And for years and years, I don't know if he thought of it independently or not, but just a few months ago, I realized that there's a paper of Motohashi where he obtains a third moment for Hecke forms for Hecke-Moss L series. But buried in that paper in a certain form is this. And buried in that paper in a certain form is the fact, exactly the same trick of transforming Kloosterman sums into Ramanujan sums and flipping them around and getting a shifted divisor function as a result. And Motohashi, I constantly get them mixed up, sorry. Motohashi says what he is doing is taking a result of Kuznetsov and just cleaning it up and removing the mistakes. He says this in a really irritable and a usually sarcastic tone throughout the course of this paper. But he cleans it up, corrects mistakes, and presents what he says Kuznetsov results should have been. And then in a later paper, this is in 1993 that Motohashi did that, many years after Goldfeld did his trick with this, but I really would love to have somebody tell me whether Kuznetsov thought of that originally, whether the idea originated simultaneously independently with Kuznetsov and also with Goldfeld, or it's conceivable that Goldfeld also did a bunch of work with. Goldfeld also read a 200-page paper of Kuznetsov in 1978 that purported to prove the Ramanujan conjecture, and discovered that it didn't prove the Ramanujan conjecture, but I wonder if it contained this little trick in it somewhere. Don't know. Anyway, the point is, what Motohashi did in his paper, what Iwicz did in his paper that follows is, they didn't have this Dirichlet series. What they had was what you'd get with this Dirichlet series if you brought the integrals, if you interchanged the summation and the integrals. And so you had a whole bunch of integral transforms of stuff that looks like this. And they were able to control the integral transforms in a way that was morally equivalent to saying, if I keep this in the range of absolute convergence, I can stop here, estimate, and go on from there. So the philosophy that we wanted to use, that we wanted to, is to say that actually, well, let me show you something actually. See, if you open up the if you open up the Kloosterman sum, you end up with a sum over alpha mod c of an e to the 2 pi I m alpha bar over c, let's see, and then we end up, then we could bring the sum over c. Sorry, this is the sum. This is the sum over m and n and c. If we bring the sum of a c outside and we bring the sum over m outside, and inside we just consider the sum over n, the sum over n has this form, e to the 2 pi I alpha n over c, a of n over n to the s plus w. And this, so here's where the trick that either Goldfold or Kuznetsov or both originated. If you take this thing and you sum over n, it's actually an additively twisted GL2L series, which you could take. If you invert, if you reflect it into its image under the functional equation, gets reflected into the same thing with e to the 2 pi I alpha bar n, and there'll be either a plus or minus sign, could be both, times a of n over n to the 1 minus s minus w, and there'll be a c to the 1 minus s minus w that comes out in front. So if you do the inner sum over this, apply the functional equation, pull out the c's, then it turns out that you could sum over the c's, get those stupid c's out of the way, and what you're left with is the alpha has become an alpha bar. Oh, sorry, yeah, this was supposed to be an alpha. Yeah, the alpha has become an alpha bar and matches up with this alpha bar. When you put them together, you end up with a Ramanujan sum, because there's no more balancing act between an alpha and an alpha bar in there. And what appears in the midst of it is a sigma is a divisor function of m plus or minus n. Kind of crazy. So here, and now, let me show you what happens after a certain amount of dust clears. So after a certain amount of dust, the object of interest turns out to be this, the sum of a of n, sigma s of 1 minus 2s of m plus or minus n, b of m over m to the w plus v, n to the 1 minus s minus v. And this is what I refer to as a triple shifted multiple Dirichlet series. And it's a sum over m and n bigger than or equal to 1 with the shift in the middle thing there. And notice when s is a half, this will become sigma 0. And it turns out that this can be analytically continued to the whole C2 plane. And it turns out And it turns out that if you look at this thing, well, if you look at just the sum over the ends, let's see what. Now, never mind. Getting too detailed. All I really want to say is that in ordinary life, what you would do is you would try to arrange your lines of integration, the u and the v, in such a way. Notice the u doesn't even enter into it here. In such a way that you get this to converge absolutely. And that usually controls where you stick your lines. But imagine how much better it would be if instead you could move your lines of integration passing over all the poles of this thing, picking up residue terms that you understand exactly, and pulling the lines of integration over to a place where you could estimate them easily as just being nice and small. And so you end up with a tremendously precise description of this as main term plus error term. Believe it or not, even though it's a shifted Dirichlet series, there is a main term coming from the continuous part of a Kuznetsov trace formula, and is an error term. And so it's that refined method of looking at things that seems, as far as we can tell, to give us results that are good enough to be, to me, disconcerting. And I think I've said enough, so I will stop.
Where do you get your new estimates from?
Oh, the new estimates come from being able to understand the right-hand side as main term, which will be t squared to the right-hand side turns into main term, which is in two pieces, each of the form t squared times a power of log p. There's one piece like that coming from the diagonal term, another piece like that coming from the off-diagonal stuff. Then all the rest is what you want to control as an error, and all the rest turns out to be on the order of t to the 1 plus epsilon. It's just very hard to see that it's really an error unless you use the meromorphic behavior of that multiple Dirichlet series. Yes? Oh, as a matter of fact, I fully expect to be able to do this with A and B replaced by an Eisenstein series at a half. And you would get an eighth, well, you would get a, but yes, you would get we would get an estimate for L half uj to the fourth as t squared times log t to some power plus an error. And I'm not sure yet what the error would be, but it seems likely that the error would be enough to give a t to the 1/4 bound for L of a half u sub j. I believe, but I'm not promising that by any means, because the moment you start fooling around with Eisenstein series, these already unpleasant objects become even more unpleasant.
Any other comments, questions? Any improvements? No.
Anybody find any mistakes?
Not yet.